Okay, good afternoon, everybody. People are still coming in, so around 34 people. So we'll start. So today we are going to do the second all pairs shortest path algorithm, which is called the Johnson's all pairs shortest path. So, what is this algorithm? We've already discussed Floyd Warshall, and what happens in Floyd Warshall is that we are doing calculations based on bottom up approach where we introduce one vertex at a time in the intermediate path and then find whether the previous distance was better or the introduction of an intermediate vertex gives a better distance. Better would mean minimum distance. And you saw there was three for loops all running from 1 to n on the adjacency matrix giving a runtime of vq. So using Johnson's, you can reduce it to v square log v plus ve. And in case your graph is a complete graph, so if you remember, we discussed it that if it is a complete graph, then you have the number of edges is equal to v square. Okay, so if you replace that here, you get v cube plus, you can say e log v. Okay, so this is the maximum of the two. So the runtime for Johnson's also becomes v cube if it is a complete graph. So it gives you a good runtime only when you have a sparse graph with not v square number of edges. So what does Johnson's algorithm do? It uses two algorithms together to find we know Dijkstra's and Bellman-Ford, they give us the shortest path from source to any other vertex, right? So but here we need all pairs shortest path. So what we do is we use Bellman Ford to eliminate negative edges from the graph because Dijkstra's doesn't work on uh, negative weights. So to eliminate negative weights, Bellman Ford can detect negative cycles and it can work with negative weights. So we use Bellman Ford to remove the negative weights from the graph, and then we apply Dijkstra's algorithm for all the vertices in the graph. So if you see the runtime as mentioned here is v square log v. For Dijkstra's algorithm, you have a priority queue or a heap where you take out for every, you maintain a queue and then you extract one by one. So you have log v is the time taken to add or remove from a heap because that's the height of the tree that gets readjusted. So v square log v is the time for Dijkstra's and ve time is for, so v times v log v, that is your Dijkstra's algorithm. Okay, and Bellman Ford is ve. So v times v log v. So it combination of these two gives you a good you can say good time saving over Floyd Warshall. So we need to remove all the negative weights. We have to basically reweight. So one intuitive approach is that you add a distance. So let's see a graph here first. Okay, yeah. If this is your graph, the intuitive way of removing a negative edge is that you add what is the highest weighted negative edge in my graph? It is -5. So if I add +5 to all edges, so intuitive is that it should eliminate the negative edge, but it will actually create problems. You are not uh, increasing the weights proportionally of all the edges. So if let's say the shortest path from 0 to 2 was 0 1 and 0 1 to 2 initially, so that was for a total of -1. Now Shortest path from 0 to 1 to 2 based on this new plus 5, it is going to be 9. So you see, we have added only 5 to the edge, but we are adding mm, almost 1 9 plus 1 10 to the actual shortest path. So it does not remain uniform. So we'll see that in a while. So just a second. So let's go back. Okay, so first we have to learn how to transform the given graph with negative weights to all non-negative weight edges. Okay, so just like I said, you to eliminate negative, you can add the highest. You find the highest negative as in the least value of the edge in minus, and you use the you basically just balance it to 0 and then add the weight to all the other edges. So if there are multiple paths from a vertex, then all the paths must be increased by the same amount, so that it's like unless you increase all the paths with the same amount, there will be a discrepancy in the shortest path in the changed graph. So we want the shortest path to remain the same for the vertices even after this weight change, but if you add it to every vertex, it will not be uniform. So the idea is to, instead of doing anything with the weight, what Johnson's algorithm does, it assigns a weight to every vertex, and then it uses this weight to reweigh the edges using the vertex weights. So the formula that is used is that the weight of the edge, weight of uv, is changed to weight of uv plus hu minus if the edge is u to v, then so it's like this. If the edge is u to v, the weight is, this is the weight of this edge between u to v, we assign a weight or a value to the vertex. So then we add this difference between the two to your weight, and this will be your newly changed weight of the edge. So how this works is, let me show it here. So you have u v w. Okay, so we'll assign hu. We'll see how we will assign this. So what is the new weight here? New weight here is weight of uv plus hv minus hu. So this is for this edge, and for this edge it is weight of vw plus hw minus hv. So this is for the path between u to v, and this is for the path between v to w. So for the entire path between u to w, if you add these two, so you get let's say this is w1 and w2. So w1 plus w2 plus hw minus hu. So your the proportion is the same. So when you're not adding anything extra to the path from u to w, because this hv, it is present in both the incremented weights of the edges, and it gets deleted. So the weight changes uniform. It is not this, you don't add hv twice. In the previous case, when we were doing, let's say this was -2 and this was 4. Okay, so we want to eliminate this. We'll add 2, it becomes 0. We'll add 2, it becomes 6. Okay, so the overall weight is 6. So you're adding 2 twice, and sometimes this thing can affect the shortest path, some maybe some other path which was not the shortest path but it had only one edge, there you'll have only an increment of 2. Here you are having increment of 4 because there are two edges in the shortest path. So that might cause the shortest path to change. Here, because of this formula, this intermediate ones are eliminated. So however long the chain is u, v, w, x, y, z, all the intermediate ones will be eliminated. So you'll only have the weight difference of the last node and the first node. So coming back here, we'll see how we get these weights of the vertices. So this is what I explained. Or the non-negative edges will become positive by this, and because you have this minus factor, when you do it for all the vertices in the path, in any shortest path, the intermediate ones will get cancelled. Now, how do we calculate these weights of the vertices? Okay, there's nothing called weights of the vertices. We are just in this algorithm, they're introducing this concept to eliminate negative weightages. So they use Bellman-Ford algorithm. What they do is they add a new vertex to the graph, and you that will kind of be the source vertex, and there are only outgoing edges from the source vertex the to all the other vertices of the graph. So let's see if there is a so it's something like this. Okay, so first thing is you add a node number 4 as a kind of source vertex, and there are only outgoing edges from this to all the other vertices, and you assign a weight of 0. Okay, and nothing changes in the graph. The original graph is the same. This brown ones, they are the additional edges which we are just adding to calculate weights of the vertices, and after we are done we will eliminate or remove these extra edges. So the algo goes like this. We first do the step of adding a new source vertex, and we modify the graph. On the modified graph, we add, we perform the Bellman-Ford algorithm. Okay. If there is a negative weight cycle, if at all there is a negative weight cycle, because we have eliminated all the negative edges, even if after that there is a negative weight cycle, it will return. But that will not happen because this new vertex, either was a negative weight cycle earlier, but this vertex will not because cause any negative weight cycle because it has only outgoing edges. So once you run Bellman-Ford, so the distances that you get by calculating Bellman-Ford, that is the distance from this new source to all the vertices of the graph. So Bellman-Ford is a single source shortest path to all the vertices of the graph. So our source is the newly added extra node, and we run Bellman-Ford and we calculate the distances. These distances will be the weights of the new weights of the vertices. So once we are done, we get the weights, the distance, we get the weights of the vertices, and then we reassign or modify the original weights of the edges using this formula which we were discussing, HU minus HV plus weight of the vertex. And then once you're done, you will perform, you will run the Dijkstra's algorithm for every vertex after removing this. Let's go to the, so we'll see how it eliminates the negative edges in the example. So, okay, so this is what we do. This is our step 1, add a source node with outgoing edges to all the vertices of the graph. Then we apply the Bellman-Ford algo using that relax technique. And once you are done, you find the distances of all the vertices from the source vertex, and whatever that distance that we found here, just a second. So these are the distances we found to source node 1, 2, 3, and 4. So this is going to be your H. This no one, the nodes are 0, 1, 2, 3. So these are going to be your H0, H1, H2, and H3. So if this is your H0 is 0 and your H1 is minus 5. So what is going to be H1 minus H0? That is going to be minus 5. This minus 5 has to be added to the weight of the edge between 0 and 1. So if you go to the next slide, what is the weight of the edge between 0 and 1? It is 0. So if you see here, this one is H1 minus, this is, sorry, this is not the original graph. Just a second. Let's go to the original graph. This is the original graph. So the weight is minus 5 and your H1 minus H0 is also minus 5. Oh, sorry. Yeah. No, this, what did I do? H1, see, maybe I minus 5 minus 0. Okay. Let me just remove this. So the distances are as given here 0. So H0 is 0, minus 5, minus 1, and 0. So for the edge 0 to 1, it is minus 5 minus, there's something I'm doing wrong here. Minus 5 is the original weight plus, okay, let's do it for some other edge first. For this is for 1, 2, 3, 4. For the edge 1 to 2. Okay. No, again I did it wrong. It's just, this is edge 0, 1, 2, 3. For the edge, let's do it for 1 to 2. The weight of the original edge is 4. Then it is doing H1 minus H2. Doing H1 minus H2, which will be 0. Let's go back and see. It is, oh, sorry, it is HU minus HV, not HV minus HU. So that's why, okay, let's go back here. So it is HU minus HV, the distance, not HV minus HU. So this for 0, 1, it is original weight is minus 5. Then HU is 0 and minus H1 is minus 5. So minus plus, this becomes 0. This also becomes 0. So similarly, this is 0, this is 3, and this is 3. So these are the recalculated weights of the edges. And once you're done with that, so it is HU minus HV. Now, if you see, all the weights are positive, and now we can run the Dijkstra's algorithm. So let's run it for one vertex. Let's run it for, this is the source. You put infinity values for all the vertices in the queue, the key values. Then you DQS from the queue and you update the distance. This changes to 3. The next one, this is the lowest, so this gets DQ'd, and because of this, this distance gets changed to 0. One has only one outgoing vertex. Next, 2 will get DQ'd, and the distance from 2 to 3 is 0. So 0 plus 0, this changes to 0, and then next this will get DQ'd and you are done. So the shortest path from 0 to 1 to 2 3 is simply 0 1 1 1 2 and 2 3. So if we go and check in the original graph, so shortest distance from 0 to 1 is -5. Then shortest distance from 0 to 2 is -5 plus 4. So that is 0 1 2. Shortest distance from 0 to 3 is -1 plus 1 0. So what we get as an answer is true for the original graph. But we have just done it for one of the vertices. So you have to repeat this 4 times. So next your source will be 1, and then you will find the shortest distance from 1 to all other vertices. There might not be a path from one vertex to another vertex. In each case, the distance is infinity, or there is, you can say there is no path. Okay, so it is mixing up two algos, Bellman-Ford, to eliminate negative weight edges by using the formula weight plus HU minus HV. HU and V are the distances from the, you can say, the fake source that you add at the beginning to calculate the weights of the vertices. So complexity of Dijkstra's algo is V log V. V times you are doing NQ or DQ. Actually, when you NQ, it's, you have all the distances are set to infinity. So there is actually uh, kind of everything is at the same level. So when you DQ, whenever you DQ or update, you update it V times. We have seen there, we update it V times, so it changes to V log V. So we are doing it V times this time, so V square log V. And for Bellman-Ford, the complexity is V into E. So this is the overall complexity. And this is true only when the graph is sparse. When the graph is complete, E is equal to V square. So you will get one term as V cube, and that will be your runtime complexity. So this algo does better than Floyd-Warshall only when it is a sparse. Okay. Now, okay, here I need to edit this what I wrote. So this will be HU minus HV, and this will be HV minus HW. In any case, HV will get cancelled, and you get this as the weight of the path. This is not the actual weight. This is what gets uh, the how the paths get modified when you apply Bellman-Ford with the fake source, and this will be the weights of the paths or the edges. Now, I remember a couple of questions by a student regarding the runtime of Fibonacci series. So if you probably that student looked at the mathematical proof of how the Fibonacci series has a runtime of 2 to the power n, and that involves something which we call golden ratio in mathematics, and it is based on some characteristic equations that you have to form. So I don't know whether you've done all of that mathematics. I have done it long time back, so I don't remember. So an easier way out to uh, find what the runtime of Fibonacci series is by a recursion tree. We know what the recursion tree method is. So the tree goes like this in case of Fibonacci series. For every you have repetitions in both the branches. So that's we're not concerned about that. For example, if n is 8, you will get 7 6, and then you'll get 6 5. This will be 5 4. This will be 5 4 again. 4 3 4 3 3. Okay, कहाँ गया? Okay, I can't leave the board, so it's again 4 3. I'll just draw one side of the branch. 3 2 2 1 2 1 1 0 1 0 2 1 1 0, and so on. So what I want to show you here is that either your tree kind of finishes at level the second last level, because you always have this n minus 2 and n minus 1, and the rest will always at the most 3, because if you give the initial condition f0 is 0, f1 is 1, and f2 is also 1, or if you want to just keep that. So we when we say O of n, we are already considering the inequality. So how many steps to get to the root? Let's say this is 1 and 0 here. 1 2 3 4 5 6 7. And if you get 7 at the most, right? What is the number of nodes at this level? This is level 0, 2 to the power 0. If we take it level 0, so this is 0 level, this is 1 2 3 4 5 6 7. Okay, 2 to the power 1, 2 to the power 2. So if we go from n all the way to 0, let's say we go from 1, we go to f of 0 and f of, there's no minus 1, so we can just end there. So if we keep f0 as our base case, so overall at the most there are only 7 levels going down the tree. Let's say it is 8 for simplicity's sake and for just getting our answer in terms of n. So how many? These are the number of nodes in this level: 1 2 3 4. So at the level n, or you can say it is n minus 1, because we are starting at 0. So n minus 1, or n, let's say for simplicity n, you have 2 to the power n nodes. So that is your basically t1 or t0. Okay, so that's why you have to solve 2 to the power n t1 or t0, one of the two. Solve would mean it is a one step operation, or you have to do, when you do add of these two, you get the third term. So the complexity of this is 2 to the power n. So this is the simplest solution you can find for this. Don't go into the mathematical part, that unless you have a very strong maths background, you've already studied all of that, I don't know, maybe in linear algebra or somewhere, then you can actually understand that. Otherwise this solution would do. Okay, similarly, the other one was the towers of Hanoi problem. This is the Tower of Hanoi problem. To shift, what is the Tower of Hanoi problem? You have three, you have pegs on, you can say sticks, or what do you call them? You have to move, you have to stack them one on top of the other, and you cannot put a bigger one on a smaller one. So briefly, you have three towers A, B, C, and you have three pegs 1, 2, 3 of different sizes, and you have to move them from A to C, and B is as an intermediate. So what we do is, because we cannot put something small on top of something big. Sorry, we cannot put anything big on top of anything small. So what we do is, we first, we have to move the biggest one, this one, to C. We have to make sure that we are able to remove the top two. So how do we remove them? We take the smaller one here, the first one, and we take the second one here. Then we, so step one is to get something here, step two is to put the second one here, step three is to get it here. So what you are, what you get at the end of step three is this. Okay, now you can easily move this one here. Okay, so what does your problem, how we represent this problem recursively is that, to move the something, let's say the number of pegs is of size, that the size is 3, you have 3 pegs to remove. To move the number 3 peg, which is the largest, from A to C, you have to first move n minus 1, which is 2 pegs, from A to B. And you cannot just move them both together from A to B. You have to use C as an intermediate, like we have done here. So the problem of solving T3 is actually equal to first the problem of solving T2. So moving 2 pegs from A to B using C as an intermediate. So once you are done that, after this, now these both need to be moved here. So again, you cannot move this smaller one first. So you put this smaller one on A, and then this is on B, and then C. So to move these 2 pegs from B to C, you have to move at least one from B to A, and then from A to C. So again, your, what is your problem after moving this here? Your problem is again to move these 2 pegs from B to C using A as an intermediate. And this one is for actually the step of moving from A to C, the biggest peg. So your recursive problem is Tn is equal to twice Tn minus 1 plus 1. This one is for the nth peg, which you will move after you have removed everything that is on top of it. You will move it from A to C. Then again you are left with the problem of moving these n minus 1 pegs to the other side. So this is your Towers of Hanoi problem. So how do you solve it? We use iteration. So I will replace, what is Tn minus 1? Twice Tn minus 2 plus 1 plus 1. So 2 square. Tn minus 2 is twice Tn minus 3 plus 1. Okay. This 2 and this 1, this is 2, this is 1. So when you open this, you get 2 to the power 3 Tn minus 3 plus 2 square plus 2 plus 1. Okay. So generalizing it, 2 to the power k is T n minus k plus 2 to the power k minus 1 plus so on up to 1. Now put n equal to k. So you get t of 0. Let t of 0 is 1. So you get 2 to the power n plus 2 to the power n minus 1 plus so on. So summation of the geometric progression. So this is the answer. Okay, so which is O of 2 to the power n plus 1 minus 1, or which is O of, okay. So Tower of Hanoi problem, even if you see the recursive solution, uh, what we actually, this is a physical problem. So how we solve it is by giving the directions on what to move from where. Okay, that is actually the computer solution to Towers of Hanoi problem. We give the, we print out, move peg number one from this to this, move peg number two from this tower to this tower. So we, if you read that problem, it is simply, in English, it is, if you have to move, let's say, n number of pegs from A to C, you first have to move n minus 1 pegs from A to B. And to do that, again, it is the same problem of reduced size. Okay, it's the same problem of reduced size. So first you have to move. Yes, you can write simply 2 to the power n. It is 2 to the power n plus 1 minus 1. Yes, no issues. This is basically when we do O, we say it is for higher values of n. So minus 1 or just multiplied by 2, it doesn't make much effect. And we're not actually calculating the exact mathematical value. We just want to know what is the order of growth. We don't want to know what is the number, what you'll get if n is 52, what value you get. That is not the point here. The point is to get to know if n increases, how much longer will it take? How does the time vary as n grows or it goes to a higher value? Okay, so you have, when you have, let's say, 4 pegs, it boils down to the problem of first moving 3 pegs from A to the intermediate node, so that you can move the biggest one from A to C. But you cannot just, moving 3 from A to B is again a Towers of Hanoi problem. So it is a recursive call. How will you move these 3 from A to B? You need an intermediate, because you cannot put something bigger on top of something smaller. So you will move from A to C. These 3 pegs, you'll move them from A to B using C as an intermediate. And then once all of them are shifted to B, you will move this one peg, which is the largest, from A to C. Now, after this step, this is how it will look like. You will have the biggest one here, and you will have these 3 here. Now, again, what is the problem? The problem is moving these 3 pegs from B to C using A as an intermediate. So again, recursively, you will call Towers of Hanoi, and it will solve it for you. Solve as in, it will give you the steps to follow to solve this. Okay, so there's one more question on the, I think, the complexity of traveling salesman problem, I guess. That I will try to find an example to explain it to you. So I'll either send you a note or maybe take it up in next class. Since there is no notification about your exam, which might be because the contractual faculty more which we were trying to get, they are not yet here. So maybe there are courses where the syllabus is incomplete or they are lagging behind for midterm. It is quite possible that uh, the exam might get postponed, because I think otherwise the date sheet should have come by now, or I haven't heard of any discussions. In any case, for sure, today I'll send you what the syllabus is, and then you start preparing accordingly. You will, it's an online exam, so you will get obviously MCQs, but do expect let's say, just not a one word answer, some kind of calculation based MCQs, which might take you more than just WhatsApping what the answer choice is. Okay, so somebody has to solve it for everybody to do it right. Okay, so I'll let you know, but solve the T sheets and see if you are able to do those things. They are simple mathematical problems. You are given an equation and you have to use that to solve a problem. But the only thing is, you should understand how that equation is the solution to a particular problem and what kind of algorithm you're using in that equation. Okay, and you should be able to identify, given a problem, which category it will fall in. Okay, so Aman, can you take the attendance?
Yes, ma'am. Done, ma'am.
Done. All right, thank you. Enjoy your lunch.
Thank you.